Here we go. Okay. So now I'm doing the field theory. It's the massless field theory, so I have the same. So Lagrangian is the integral over all space at any moment of time. It's the same thing, minus 1/2 the four-dimensional gradient squared. Sorry, plus 1/2. But I'm going to now resolve it into time and space. So it's minus 1/2. This is just the spatial gradient. I don't know how to, I guess what it is. Squared minus m squared. Oh no, sorry. I have m0. So that's all. That's the Lagrangian. That's Lagrangian. Compare that to this. We're going to think of the field theory as a limit of an infinitely dense collection of harmonic oscillations. So you compare this to this, you see the GAB corresponds, it's just the identity matrix. As a matrix, it's just the identity matrix. And V, V as a matrix, well, we have to do this, we have to do this integral of the gradient of phi squared. If you do an integration by parts, that's just like phi, Laplacian phi. So V corresponds, I might get the sign wrong, I think it's right. V corresponds to the spatial Laplacian squared, right, as an operator. But what's happening here is that the indices A and B correspond to just spatial locations, x, y, whatever. Which is, so the index of the matrix is just a point in space. Sorry?
There's no boundary.
Oh, there's no boundaries. It's an infinite space. Just
Phi goes to 0.
phi, let's imagine phi goes to 0. Yeah, phi goes to 0 at infinity. So W is equal, and W, remember, was this. So since what G is really 1 in this situation, this is flat space. Had the space been curved, then it would be more interesting. G would not be just trivially identity matrix. But in flat space, it is, in Cartesian coordinates anyway. And so W is minus del squared. What does that mean? The square root of the Laplacian. Well, you can do that by Fourier analysis. And so if you write what is W as an integral kernel, then it just the Fourier analysis shows you that it's 1 over x minus y squared, which is spatial to the fourth. So, in other words, if you Fourier transform the Laplacian, it becomes k squared. And you Fourier you take the square root, and then you Fourier transform back, you get this expression for the two-point function. And for W inverse, you get, regarding it as a big matrix now, with x as the label, x and y as the label, it goes like 1 over x, the distance x minus y squared. This is just dimensional analysis. I believe that the coefficient here is actually minus 1 over pi squared, but I haven't double checked it. And I believe, yeah, it's known what it is, but I just didn't bring notes and so on. So I believe that the coefficient here is 1 over 2 pi. So you can take it with a small grain of salt, but it's just some pure number. The important thing is the scaling of 1 over x minus y squared. And what's kind of interesting, is worth pointing out, is that this is just minus, these are positive kernels. This is kind of a side note, but I think it's interesting. And people get confused about this. I won't name some names, but I know some people who I think are confused by exactly this point. Yeah?
Could you invert it in case space where it's easier to invert and then take the Fourier transform?
I think that is what I did.
Okay, you get the same answer. No,
But that's the only thing I did. I don't know how to do it directly in X
Okay,
space.
okay.
So the way I got to this formula was, in fact, though this curly f is meant to take a Fourier transform. So go from X space, this is in X space, go to K space. So the Laplacian is K squared. And its square root is easy to take, as you said. It's just the absolute value of K. then you un-Fourier transform the absolute value of k, and you get, you get the W in k space, which was this minus 1 over pi squared. Let's just call it r to the fourth, r being the distance between the 2 points. The kind of interesting thing is the minus sign here. Right? We argued before, and it was very important, that W was a positive, definite matrix, and yet here you see a minus sign. Every matrix element is negative, but of course so that looks a little peculiar, but of course what it's not telling you is what's the meaning of this thing exactly at coincidence when x equals y. That's the diagonal. And what happens is the diagonal is so strongly positive that it overwhelms all these negative numbers. And to give this a real meaning, this is not yet really defining any distribution. You have to say exactly what the nature of the singularity is at the origin. That's just, I don't want to say too much more about that. It's an interesting question in itself. This one is well defined as a distribution because it's not that divergent. And so fortunately it's got a positive coefficient. But this one is not well defined until you say exactly what's going on at the origin.
I was just suggesting that you get to square root of k squared, which is k.
Yes.
Then if you take 1 upon k, invert it in Fourier space, and then take the Fourier transform, you get the same answer as this one.
As this one?
Yes.
That's how I got this one.
Oh, that's how you got it.
Yeah, I don't know any other simple way.
Oh, I thought you were taking the Fourier transform into the wxy there and then inverting that as a...
That would be nice.
Oh.
I would do that if I knew how. But in fact, I did exactly what you said. So this came by a similar thing. Go to k squared, go to 1. But then here you put 1 over k squared, and then you undo the Fourier transform, and you get this expression.
So the corresponding potential will be square root of this.
The potential would be the square of that. So the potential was, I didn't write it, but the potential is, oh, here it is. Yeah. The potential is the Laplacian itself. Which, that's what it is as an operator. As a kernel, it's really the Laplacian of delta 3 of x times y or something like that. But as an operator, it's easier to work with it, thinking of it as an operator than this. But it doesn't matter. Either way, when you Fourier transform it, you get this k squared. Okay, so in words now, what is it that we want to do? So we want to take a half space, say z greater than 0, compute the entanglement entropy between everything, the positive z and negative z. We can analyze into modes e to the I kx times x plus ky times y. No kz, in other words, transverse modes. Each mode is its own problem that decouples from the other one. Each one of these, so for a fixed value of the transverse momentum, you get a 1 plus 1 dimensional problem that looks exactly like a massive, it looks like 1 plus 1 scalar field with mass. And it's easy to convince you, just take a minute or so, but we don't have a minute or so. So it's easy to convince yourself that it's just the mass squared is exactly given by transverse k squared. So the higher the frequency in the transverse direction, the higher the mass of the effective 1 plus 1 dimensional problem. And then you... Oh, that's meant to mean...
The vector.
That's meant to be the vector, the two-dimensional bit of the vector. So it's just kx and ky, but no kz. Kz is the remaining degree of freedom, which we can't analyze that in plain language because there's no translation invariance in that direction. But there's translation invariance in this direction. So it decouples into a bunch of one-dimensional problems. And the entropy is then, it's just the sum of the entropies of all of the one-dimensional problems. And it's integral from, then again, the area comes out very easily. And you get, other than that, you get P dt, well, no, I won't bother. It's M, using this definition of M, it's M dm S of M, where S is the entropy for the one-dimensional massive scalar field of mass M in 1 plus 1 dimension. But what I didn't tell you, where did the cutoff come in? And so the cutoff, we'll put it in the following way. It's natural in this setting to choose the cutoff in the following way. So let this direction be, say, y, and this direction be z. I won't draw x. So here is z equals 0. The region B, the oscillators I'm not going to trace over are in this region. The oscillators that I am going to trace over are over in this region B prime, the complement. If I don't put a cutoff, then I'm going to get each of these problems, these one-dimensional problems, is going to have an infinite answer. Remember, we expect the answer to be, from the previous discussion, we expect it to go like log of 1 over ml, or little l is the cutoff. So a natural way to implement the cutoff in this setting is just to hold the two regions apart. In other words, instead of computing the total entanglement between everything to the right of the plane and everything to the left of the plane, let me consider only entanglement between oscillators to the left of minus L. So in other words, just leave this little bit out and consider only entanglement between this side and this side. Now we'll get a finite answer. And so if you do that, each of these SMs is finite, but the SM is really a function of, so I set it up like this, then I do the analysis into mode, blah, blah, blah. And then this S depends both on M and L. Of course, it can only really depend on the product dimensionally. And so here's the answer. So I'll tell you, so for each of these finite dimensional problems, each of these fixed value of the transverse momentum, each of these 1 plus 1 dimensional problems, you work out what is lambda, and here's the answer. So lambda of x, y, what? I've called it z and z prime. So you see, so there's a z here, there's a z prime here, there's some other variable here. These are like the A oscillators, these are the alpha oscillators. So you're going to get the W, you're interested in the off-diagonal W, which connects this to this. So you have to take the convolution of W and W inverse. That's exactly this formula here to get lambda, where the alpha index means integrating over points to the left, and the A and B means your argument points are to the right. So you end up with this expression: 1 over pi squared integral from minus infinity to minus, I have to find one other thing, minus c of k naught of z minus u times k. What these are these modified Bessel functions? U minus c prime, z prime. U is, this is u, not y. Over u minus z prime du, where we assume that z and z prime are greater than 0. And here an integral u, and where c is equal to, I guess, is just m l. That must be what, let me just double check. That must be what c is. Yes, c is m l. So this is the mathematical problem it comes down to. You have to find the spectrum of this operator, plug it into this formula, and that gives you the entropy So this gives you the entropy associated with M. And then you just need to plug it into this integral here to get the total entropy. In order to prove, the theory of integral equations tells you a fair amount about this. It tells you that the spectrum of this is discrete, that it accumulates at zero, so the eigenvalues are getting smaller and smaller and smaller, going to zero. Otherwise, the spectrum is discrete, tells you you can work out easily bounds on the eigenvalues. So the general theory is enough to see, or to almost prove, that this S is finite. Once you know that S is finite, then the area law follows. You need to show that this integral also converges, so you need to know that S falls off rapidly enough at large mass. That's sort of obvious, although I haven't actually proved it. It's sort of obvious from the fact that these things fall off exponentially at large separation, these modified Russell functions. So that's
this area, the area that you have is formally infinite, because
it's formally infinite, yeah. So this is really it's better to put it on this side, I suppose. So what we're really computing is the entropy per unit area of this infinite plane. Yeah, that's right. It's formally infinite. So I think the problem that I had, not the homework problem, but the research problem that I had in mind was just to analyze this operator. So for this, given this integral kernel, there's like 5 subproblems, which is one. So this is problem. Prove. So just a succession of better and better things. First of all, prove that lambda sub n goes to 0 fast enough such that the entropy of C or M is finite for all M, for all positive M. 2 was prove that the entropy itself as a function of M goes to 0. The thing that I said was more or less obvious. As M goes to infinity, that means as the transverse momentum is going to infinity. This is all in the presence of a fixed cutoff L. Then 3 was evaluate this integral from 0 to infinity of, I might as well call it M dm. I called it C, but anyway, yeah. I'll call it C because it's a dimensionless number. C dc S of C. I'm mixing up the notation a little bit. This C, remember, is just ML. It's a complementary thing, it's a cutoff of the inverse. And then 4 was find C, which I erased what it was, but we will get, so I guess this is what I call there's actually an L squared here that I should have written. And then if I call what's left over C, that it's the same coefficient that the entropy is equal to C times the area over L squared. This was all in 3 plus 1, of course. Find C in that formula. Well, in the formula that S is approximately equal to C and L squared. And then finally, it was evaluate. What did I do? 4 and 5 were the same. So there is no 5. So that, in other words, if I don't. I numbered them wrong. This was for evaluate. This was for, which is the same as finding C. And 3 was something else that I didn't read properly. Yes, which we believe that needs to be, from this point of view, proved independently. Prove that S of C scales as, maybe I should call it, C prime, some other constant log, although they're related, 1 over C as C goes to 0. So that should have been 3. So 2 was asking what's the behavior of this, I messed up, C and M, so sorry. Just take wherever you see C put M or vice versa as you like. So the number 2, so number 1 was saying that the entropy is well defined. Number 2 was saying that it goes to 0 at M equals 0, so that it is fast enough so that it can be integrable. In fact, it doesn't even have to go to 0, but it should come in as 0, so it can be integrable. And then 3 was, infinity. So that this integral can converge. 3 was saying, find its behavior. Let me go back and say it again. So you want this integral to be finite so that you can get an area of finite entropy once you put in this kind of cutoff. So it has to neither diverge at its upper limit nor at its lower limit. 2 and 3, we're just asking you to show that. But in the case of 3, we actually know what we believe the behavior should be at the lower limit. So, sorry, at the upper limit, we don't have to be I don't know. I'm getting mixed up here, so rushing too much. But anyway, it's just to analyze the behavior of this integrand at both the upper and lower limit. And then the last one was just to find the actual value of the coefficient, to do the integral and find the actual value of the coefficient. If you want, I can more carefully go through and not correct probable states in what I wrote here. But the idea is just what I said. And then there's a homework problem. The homework problem is consider a crystal using everything we've done. So just for your own amusement, but estimate the entanglement between 2 halves of a crystal in its ground state. In bits per cubic centimeter, square centimeter, if the lattice spacing is about, say, 5 angstroms, and the speed of sound is about 5,000 meters per second. So,
what happens to your question number 2 in 1 plus 1 dimension? Naively the argument that you gave is log of 1 over ml, so if I take n to infinity, it seems like we go to minus infinity.
Right, so there's enough, that's right. So if I were to take m to infinity, so I'm dealing with that's a good question. So I'm dealing with a very strange situation where I have this sort of intermediate layer that I've put in, and I'm taking something whose wavelength in the transverse direction is much, much shorter than the separation between those two things. And so in that limit, the mass is then much, much greater than as you said, ml becomes much greater than 1. So in that limit, the estimate that means that the quantum wavelength is much, so it means that you're really a great distance apart compared, your cutoff has made it almost impossible for such a mode to get from one side to the other. And I believe what happens in that limit is that the entropy actually falls off exponentially. So this asymptotic form is completely wrong. And that's ultimately because these Bessel functions themselves, most of the Bessel functions that go to this integral fall off exponentially with distance. So if I had said this right, which I'm not at all sure I did, it's one of these parts of this homework, of this research problem.
Let's go.
Power's off for now. They'll probably come back. Oh, yeah. Well, that's true. I don't know. Do we have, oh, you still have Apple Vacation? I don't know.
Blackboard's come back.
Background. Well, that's really all I wanted to say. So, unless there's questions.
I had one question, which is I think
There we
it's a
go.
basic confusion, which is that formula where you write it down as s upon a as upon s squared. So when you express everything as an integral
This
of
one here?
yes. Where did the, I mean, so this is a crucial part. How did
Yeah, that's a crucial part, and I skipped over it.
Yes, I don't know. I mean, so that's where the area comes in because, I mean, here you have your lambda, and I can go from that point to, I mean, if I could solve this eigenvalue problem, then I would stick it back in there and I would get something. And then from that, I could deduce, presumably, that the area piece comes out of just that, right?
Yeah.
Summing over all
Yeah, in the end, it's just dimensional analysis, roughly speaking. You just plug, once you assume that this is finite, then this follows. So I'm trying to think how, I mean, I have the calculation here, so if you want, I can just put it on the board. Should I do that? Or should we give people a chance to leave and then discuss more?
Either that or, I mean, we've already scanned your notes from the previous week. If you just give us your notes.
Okay, these notes are an utter mess for today, but I can write them out a little more
Okay.
neatly.
Maybe that would be a more efficient way then, and if you could have them online later then. Okay, so you're saying that there is a careful calculation.
There is
so
a,
we just
yeah,
have to follow
there is a
it.
perfect one.
Any other questions?
I mean, there's this way of doing calculations in quantum field theory for the entanglement using this replica trait.
Right.
What is your opinion about this replica trait?
So I guess I think there's different things that are related that people call replication. One of them is just asking what's the response to a canonical a small canonical singularity. I think that's probably completely valid, at least at a formal level. The caveat that always has to be put in is how did you put in the cutoff? Is it valid or is it sneaking something in? But most people who think about such things have come to the point of view that it doesn't really matter much how you put the cutoff, you're going to get the same general behavior. That seems to be borne out by experience. In this case, I always feel more uneasy because the way that it's usually put in and the way I did it here also, it badly breaks Lorentz invariance, and so you feel, well, if I did it in a different frame, I might get the same dependence, but I might get a completely different coefficient. I always have that uneasiness, but modulo that uneasiness, I think that that's probably a perfectly valid way. There's another way where you actually just compute 1 copy, 2 copies, 3 copies, 4 copies, and then you sort of do an analytic continuation. So if it's justified, I don't know why it's justified. I mean, it's not crazy. It's obviously a sort of sensible thing to try, but if you force me to justify it, beyond saying that it looks like a sensible thing to try, I wouldn't know how to do it. Maybe someone else does, but obviously you can't. I mean, you're asked to take a function knowing it's just an integer argument and compute its derivative around n equals 1. That seems like a very ill-defined problem.
That's what I was asking.
Yeah.
You see, in this model, from what I understand, you have the ground state depend all over space.
That's right.
Then one is simply looking at 1, 2 halves.
In this case, in the simple case, right, I just
In all the
said
cases,
a half space.
Now, whatever it is, one region and its complement.
Yes, right.
However, there is another situation where maybe they can give there may be the interface of, for example, two media, or like in the Josephson junction.
Oh, so where it really is,
Huh?
where there really is some physical
There's something
demarcation
happening.
between
Then,
the two.
then the story is somewhat different. In the on and off section in the layer we have discussed.
So why is it different? I mean, as far as
Because-
the general thing, I don't see any difference.
Because the ground state, then on one side, for example, the operator, the Laplacian writing, will not be self-adjoint. It will have some division series at the boundary. The other side will be complementary division series. And there will be some